Over the next hour, I'm going to take you on an immersive journey to explore. If the world we live in is actually a simulation, why can't we feel it? Feel free to like and save this video, and get yourself into a comfortable position. Have you ever had one of those moments? You're lying in bed, staring at the ceiling, and a thought suddenly pops into your head. What if this world is fake? What if everything you see is just a program running inside some supercomputer? Your memories, your emotions, your thoughts, they're all just lines of carefully written code. That thought makes your heart race. And then you roll over, telling yourself to stop overthinking it. You pinch your arm. The pain feels real. You listen to the sound of the wind outside. It's real. You think back to the bowl of noodles you ate today. Those chewy noodles, they're real. Everything is so real. How could it possibly be a simulation? But that is exactly the point. If there were a computer powerful enough, why would the world it simulates have to make you feel that it's a simulation? Think about the video games you played. 20 years ago, game characters were just a bunch of pixelated blocks. 10 years ago, they became somewhat stiff 3D models. Today, you can see visible pores and pupils that dilate and contract with the light. If it continues to develop at this speed, in another 50 or 100 years, if the precision of simulations can be improved infinitely, then one day, the simulated world will be completely indistinguishable from the real world. And if you can't tell the difference, how do you know that day hasn't already arrived? Aren't you, right now, inside that very simulation? Tonight, let's get serious. We're going to break this problem down, layer by layer. If the world really is a simulation, what kind of tricks could it possibly be using? How could it fool the eyes of 8 billion people on Earth, making everyone believe, without a shadow of a doubt, that they are living in it? It might be much deeper than you imagine. We'll start 2,400 years ago in an ancient Greek cave, passing through the study of Descartes, following Bostrom's probabilistic arguments, journeying through the eerie world of quantum mechanics, and descending into the abyss of a mathematical universe, before finally falling into a quiet sleep under the starry sky. Are you ready? Then, let's set off. Chapter 1. Plato's Cave. The first question asked 2,400 years ago was far older than computers or virtual reality. To trace it back to the source, we need to return to ancient Greece 2,400 years ago. To a story told by a philosopher named Plato. Plato wants you to imagine a scene like this. They are chained up deep inside a cave. They face the cave wall and cannot turn their heads. Behind them, there is a fire. And between the fire and these prisoners, people are walking back and forth, carrying all sorts of things. Puppets, animal silhouettes, various objects. The firelight casts the shadows of these things onto the wall in front of the prisoners. To these prisoners, who have never seen the world outside the cave, the shadows on the wall are the entirety of the reality they know. They would give names to the shadows, study the patterns of the shadows' movements, and build a science based on shadows. If the shadows appeared repeatedly in a certain pattern, they would call it the laws of nature. One prisoner is freed from his chains, seeing the firelight for the first time, and the objects that create the shadows, because the firelight would sting his eyes, which had grown accustomed to the darkness. And everything he sees challenges everything he has ever known about reality. Upon seeing the true sun and real trees, he comes to realize that his entire life up to this point was lived under a misunderstanding of shadows. This is Plato's famous allegory of the cave. 2,400 years ago, this ancient Greek philosopher was asking the very same question that we are asking tonight. How do you know that what you see isn't just a shadow? How do you know that what you perceive is reality isn't just a projection of a deeper, underlying truth? How do you know you aren't that prisoner bound in the cave? The reason Plato's allegory of the cave still resonates so deeply after 2,400 years is that it is still so mind-blowing. It reveals a fundamental philosophical dilemma. All of our knowledge about the world must be acquired through our senses. Our eyes see, our ears hear, our skin touches, our tongues taste, and our noses smell. But our senses only ever provide us with appearances, never the things themselves. The color red you see is just your eyes responding to a specific wavelength of electromagnetic radiation. It is just your eardrums perceiving vibrations in the air. You feel that the table is hard. But that is just your skin reacting to the electromagnetic repulsion between atoms. You have never actually touched the object itself. You are always just experiencing your nervous system's translation and interpretation of external stimuli. This means that, between you and true reality, there is always a layer of translation, your senses and your brain. And if someone could perfectly control that translator, by feeding it carefully crafted false signals, you would be completely unable to tell the difference. Just like the prisoners in the cave, their eyes were working perfectly fine. They just had no way of knowing what they were seeing. You were being manipulated all along. Your very body might be fake too. Following that path, the idea that the world might just be an illusion. 17th-century French philosopher René Descartes proposed the famous evil demon hypothesis. Perhaps there exists an all-powerful demon, with the ability to conjure an entire false world, just to deceive you. You think you have a body, but it's all just an illusion created by that demon. So, what can you even be sure is real? Descartes' answer was that legendary quote, "I think, therefore I am." At the very least, that I who is being deceived, who is doubting, who is thinking, must actually exist. Otherwise, even being deceived wouldn't be possible. 20th century American philosopher Hilary Putnam translated Descartes' evil demon hypothesis into the language of modern science, proposing the famous brain in a vat thought experiment. A mad scientist takes your brain out of your skull, puts it into a vat filled with nutrient solution, and then uses countless wires to connect your brain to a supercomputer. It sends meticulously designed electrical signals to your brain, simulating every single sensory experience in your daily life: sight, hearing, touch, taste, and smell. You see the blue sky and white clouds, hear the birds chirping and insects buzzing, feel the gentle breeze against your face, and taste the flavors of your breakfast. But all of this is just electrical signals sent by the computer. Your body doesn't exist at all. You are just a brain floating in a nutrient solution. Are you not a brain in a vat? The answer to this question is deeply unsettling. No, you can't be sure. Because every tool you use to verify reality, your senses, is precisely what's being manipulated. You could perform a scientific experiment to test what's real, but the results of the experiment could be manipulated too. Even if you went and asked someone else if we are brains in a vat, that other person could easily be a simulation themselves. You're attempting to verify the reality of the system from within the system itself. Logically speaking, that's just a closed loop. The brain in a vat thought experiment reveals a core point of our topic tonight. The reason a perfectly simulated reality can fool everyone isn't because it does certain things exceptionally well. It's because it controls the only tool you have to judge what's real, your own brain. As long as the simulator can perfectly control the signals your brain receives, your brain has no way to detect any anomalies from within. This isn't just a technical issue. It's like a perfect referee. If the referee has been bought off, then there is no way to guarantee the fairness of the game. Because you only have that one referee. But wait, we don't just have one brain, do we? There are 8 billion brains on Earth. If the world is a simulation, wouldn't it be much harder to fool 8 billion people at the same time? This counter-argument sounds reasonable, but in reality, it actually exposes a common misconception we have about the concept of simulation. We tend to unconsciously use our current level of technology to gauge the difficulty of a simulation. 8 billion brains sounds like a lot, but to a supercomputer, with processing power beyond anything we can imagine, this number might be just like our computers right now, running 8 billion simple programs at once. Maybe it's not really a challenge at all. More importantly, if those 8 billion people are themselves just part of the simulation, then the simulator doesn't need to fool them at all, because they are just products of the simulation. Fooling a character versus rendering one. That's an entirely different story. Chapter 3. Nick Bostrom's Trilemma. It's all about probability. These are all philosophical ideas, but you might feel they're too detached from real life. The argument I'm about to introduce is different. It's actually a rigorous probabilistic argument. It comes from an Oxford University philosophy professor, Nick Bostrom. He proposed it in a paper published in 2003. This argument is sometimes called the simulation argument, and sometimes it's referred to as Bostrom's trilemma. Bostrom's argument is based on 3 premises. First, consciousness can be computationally simulated. If you can simulate all the neuronal activity of a human brain on a computer, then this simulated brain would have the exact same conscious experience as a real one. It would think, feel, remember, and dream. And it would be absolutely convinced that it's real. In philosophy, this assumption is known as substrate independence. Consciousness doesn't depend on a specific physical substrate, whether it's carbon-based neurons or silicon-based chips. As long as the computational process is the same, consciousness emerges. A sufficiently advanced civilization, what Bostrom calls a post-human civilization, would possess astronomical levels of computing power. Just think, human computing power has grown by about 1 trillion times over the past 50 years. If this trend continues, in a few hundred or a few thousand years, the computing power of human civilization will reach a level that is completely unimaginable to us today. Using that kind of computing power to simulate a world like Earth, including 8 billion conscious inhabitants, is physically entirely feasible. Third, if such a simulation is feasible, a post-human civilization might, for various reasons, want to run such a simulation, maybe for scientific research purposes, to understand how their ancestors lived. Maybe just for entertainment, just like how we play simulation games today. Or maybe out of philosophical curiosity, to test what would happen if history had taken a different path. What kind of hypothesis would it be? Bostrom arrived at a deeply unsettling conclusion. At least one of these must be true. Almost all civilizations that reach a human level of intelligence go extinct before they ever reach a post-human stage. Intelligent civilizations have an incredibly high rate of self-destruction. Post-human civilizations, even though they have the power to run simulations, almost all choose not to do so. Perhaps it's because of moral concerns. Or maybe it's just a lack of interest. Third, we can be almost certain that we are currently living in a computer simulation. Why? The logic is actually quite simple. If the first two propositions are false, if some civilizations really do manage to reach a post-human stage, and they really do run simulations, then the number of simulated universes they create will far exceed the number of real universes. If a single post-human civilization runs 1,000 simulated universes, and each of those universes has 8 billion conscious inhabitants, then the number of people in the simulations would be 1,000 times the number of people in the real world. For any randomly selected conscious individual, the probability that they are in a simulation is 99.9%. That is far greater than the probability of living in the real world. Bostrom himself has said that he doesn't actually believe we are living in a simulation. What he's saying is that among these three options, we have no sufficient reason to rule any of them out. The true power of this argument lies not in proving that we are in a simulation, but in the fact that it proves we have no reason to be certain that we are not. This is a subtle but important distinction. Tesla and SpaceX founder Elon Musk was once asked about this topic. In a public interview, his answer left everyone in the room stunned. He said the probability that we are not in a simulation is likely only 1 in 100,000. His reasoning was, just look at how gaming technology has advanced in the last 40 years. Into a fully immersive virtual world. If this pace of progress continues, then creating simulations indistinguishable from reality. And once such technology emerges, the number of simulations will quickly far exceed the number of real worlds. So from a purely statistical point of view, it is much more likely that we are in one of the countless simulated worlds, rather than in the one and only real world. Chapter 4, Your Senses. A sophisticated translation machine right now. Let us answer the core question of tonight. If the world is truly virtual, why can't we feel it? To answer this question, reality is a quality that cannot be forged. But neuroscience tells us a completely different story. The reality you experience is a model constructed by the brain based on sensory input. That's right. Your brain itself is running a simulation. A simulation of the outside world. Let's start with vision. You think you see the world, right? But the actual process is far from that simple. Hitting the photoreceptor cells on your retina. These cells convert light signals into electrical signals, transmitted to the visual cortex at the back of the brain. Then the visual cortex takes these electrical signals and performs a series of extremely complex processes, ultimately constructing the three-dimensional, colorful, dynamic world you see. Pay attention to the key point of this process. It has never directly touched the outside world. It is trapped in the darkness of your skull. All the information it receives is just streams of electrical pulses. To guess what the outside world looks like, and then build a subjective experience for you. To render a three-dimensional scene, are essentially no different. This internal model built by your brain. The answer is that it is far less accurate than you think. The brain, in order to save energy and improve efficiency. For instance, there's a blind spot right in the center of your retina. Exactly where the optic nerve passes through. But you never even notice it, because your brain automatically fills in that blind spot. Or consider this. The edges of your vision are actually incredibly blurry. Yet you feel like you're seeing a perfectly clear, stable image, all because your brain uses rapid, darting eye movements to constantly sample the world, stitching it all together into what looks like a complete picture. Then there are all those optical illusions, like colors looking different just because the background changes, or lines appearing to be different lengths, simply because the arrowheads at the ends point in different directions. All of this proves that the world you see isn't a faithful, objective copy of reality. It's actually an interpreted version that your brain constructs based on its own set of rules. It's exactly the same for your sense of touch, hearing, taste, and smell. You think water is cold, fire is hot, stones are hard, and cotton is soft. But none of these are inherent properties of the objects themselves. They are simply your nervous system's subjective translation of different physical stimuli. Temperature is just how violently molecules are moving. Cold and hot are just your skin's temperature. Receptors reacting to that molecular movement. Hardness is just the strength of electromagnetic forces between atoms. Hard and soft are just your pressure. Receptors reacting to those electromagnetic forces. Sound is nothing more than vibrations in the air. Whether it's melodic or grating, that is entirely a subjective judgment made by your auditory system. And even without any input from the outside world, your brain can conjure up complete sensory experiences out of thin air. It does this every single night. When you're dreaming, you can even smell scents and feel sensations of touch. You believe, with total conviction, that it's all real. You never suddenly stop in the middle of a dream and think, wait a minute. All of this is just something my brain is making up. So, what method could you possibly use to prove that you aren't dreaming right now? You might argue that when you dream, the logic is all messy, and the scenes don't connect. But that just means the dreams you've had before simply weren't realistic enough. It's often said that the brain can't produce a perfectly logical, detail-rich dream. The ancient Chinese philosopher Zhuangzi once told a story. One day, he dreamed that he had turned into a butterfly, fluttering about freely among the flowers. Was it Zhuangzi who dreamed he was a butterfly? Or was it the butterfly dreaming it was Zhuangzi? This story from 2,300 years ago mirrors the simulation hypothesis we're discussing today. It's all generated. So, when you say the world feels real to the touch, the internal model my brain constructs is self-consistent. But self-consistency doesn't equal reality. A simulation designed well enough, a simulation capable of feeding completely consistent false signals to your nervous system, will likewise produce a perfectly self-consistent subjective experience. The mind. It's not because there is some unbridgeable gap between true and false, but because the tools you use to distinguish between them are themselves part of the system. Chapter 5. Quantum Mechanics. If the previous philosophical and neuroscientific arguments weren't enough to make you doubt reality, then this next clue from physics might truly shake your convictions. Because this doesn't come from a philosopher's speculation, but from repeatable results in the lab, verified countless times over. It's the most bizarre phenomenon in quantum mechanics, the one Albert Einstein refused to accept until his dying day. Quantum superposition and observer collapse. Let's start with the most famous experiment, the double-slit experiment. The setup for this experiment is quite simple. You have a screen with two parallel slits cut into it. And then you fire particles at the screen. Like electrons. Behind the screen, you place a detector to record exactly where the electrons hit. If you leave both slits open, and don't observe which slit the electron actually passes through, then an interference pattern will appear on the detector. A series of alternating bright and dark fringes. This kind of pattern is a characteristic behavior of waves. It shows that electrons behave just like waves. They pass through both slits at the same time, and then interfere with themselves. But here is where things get weird. If you place a detector next to the slits, trying to observe which slit the electron actually passes through, the interference pattern disappears. The electron suddenly starts acting like an ordinary marble. obediently passing through only one of the slits, and leaving just two simple stripes on the detector. When you're not looking, it's a wave. The moment you observe it, it becomes a particle. It's as if the electron knows it's being watched. This result has puzzled physicists for nearly 100 years. There are many interpretations of its nature. Yet none of them satisfy everyone. But some people, including some serious physicists, have proposed a chilling interpretation. Perhaps this observation effect in quantum mechanics is actually a clue that our world is a simulation. How do we understand that? Imagine you're playing an open-world video game. The game's world is massive, and it's impossible to render every detail at once. So, the game engine uses a very clever strategy. It only renders the part of the scene you're currently looking at. Those buildings behind you, or the street you haven't walked down yet, don't need to be rendered for the time being. They just exist in the background in a blurry, simplified form. Only when you turn your head to look at them does the engine instantly render them in high definition. In the gaming industry, there's a specific name for this. Or more broadly, it's called on-demand rendering. When electrons aren't being observed, they behave like waves. That is, a blurry, probabilistic state. Only at the moment they are observed do they collapse into a definite particle, appearing at a specific location. Doesn't that sound just like the universe is rendering on demand? The particle doesn't need to have a definite position. It's just a cloud of probabilities. A fuzzy state that saves on computing resources. Only then is it forced to render a concrete result. Of course, I need to be completely honest here. This interpretation is controversial. The mainstream physics community has various interpretations of the quantum measurement problem. The Copenhagen interpretation, the many worlds interpretation, decoherence theory. Not a single mainstream interpretation requires the reason that we're living in a simulation to explain the collapse of the wave function. The so-called observation does not require a conscious observer. Any interaction with the environment will cause the quantum state to decohere. A detector, an air molecule, or even the interference of a single photon is enough to break quantum superposition. But even so, this coincidence is still worth noting. If you were designing a simulated world, in order to save on computing resources, what would be the smartest thing to do? It would be to calculate the details only when necessary. And the picture painted by quantum mechanics is precisely that. The universe seems to decide on the details only when it needs to. This might just be a coincidental analogy, but the precision of this analogy is enough to send a chill down your spine. Number 6. The speed of light, the Planck length, and the resolution limit. Does the universe have hardware parameters? If the universe truly is a simulation program, then it must be running on some kind of hardware. And all hardware has its limits. Just like any computer screen has a maximum resolution. Does our simulated universe have some kind of resolution limit as well? Interestingly enough, our universe actually seems to have one. First, there's the speed of light. The speed at which light travels in a vacuum is about 300,000 kilometers per second. This is the absolute limit for the speed at which any information or energy can travel in the universe. Nothing in the universe can exceed the speed of light. This isn't just a technological limitation. It is a fundamental constraint of physics itself. Mainstream physics provides a perfect mathematical explanation for this. Albert Einstein's theory of special relativity proves that, as an object's speed approaches the speed of light, its mass tends toward infinity. Therefore, it would require an infinite amount of energy to reach light speed. But if you think about it from a simulation perspective, there is another way to interpret the light speed limit. In any computer simulation, the speed at which information can travel is limited by the processor's speed. A processor can only perform a limited number of operations per clock cycle. So, the speed at which information travels from one point in the simulated world to another might just be the processing limit of our simulated universe. It wouldn't be an inherent requirement of physical law, but a hardware limitation of the computer running this simulation. Then, there's the Planck length, which is about 10 to the power of negative 35 meters. This is the shortest distance that has any meaning in physics, at scales smaller than the Planck length. Our current physical theories, including general relativity and quantum mechanics, all break down. Space at this scale is no longer continuous, but instead presents a discrete, granular structure. The same goes for Planck time, which is about 10 to the power of negative 43 seconds. This is the shortest meaningful interval of time in physics. Continuous versus discrete. This might be the most fundamental difference between a real universe and a simulated one. In our intuition, real space should be continuous. You would think you could take any distance and divide it infinitely, but quantum mechanics and quantum gravity theory tell us that might not be the case. At the most fundamental level, space and time may be discrete, pixelated, just like a digital screen if you look at it closely enough. Will reveal individual pixels and discrete spacetime. That is actually a classic feature of digital simulation, because any digital computer can only process discrete data and cannot handle truly continuous quantities. Now, think about those constants in the universe. The speed of light, the gravitational constant, Planck's constant, the fine structure constant. These numbers determine every physical law of the universe. Yet no one knows why they are exactly what they are. Physicists have spent over 100 years trying to derive the values of these constants from more fundamental principles, but they haven't succeeded yet. They look like, forgive me for putting it this way, like parameters manually entered, just like the global variables that a programmer defines at the start of their code. Why is the speed of light 299,792,458 meters per second instead of some other number? Perhaps it's just because the person who wrote this code happened to set it to that value. John Barrow, a famous British cosmologist, even made a bold prediction. If we are living in a simulation, we might be able to observe physical constants drifting slightly over time, because even the most precise simulation programs might have tiny cumulative errors. These errors, after running for a long time, could cause the parameters to shift slightly. If we find that a certain physical constant has undergone a tiny change over a scale of billions of years, that could be evidence that the simulation is experiencing rounding errors. There are indeed some astronomical observations suggesting the fine structure constant might have changed by an extremely small amount over cosmic history. But these observations still carry a great deal of uncertainty and are far from being sufficient as evidence for a simulation. There's another phenomenon worth pondering: the fine-tuning of the universe. Physicists have discovered that the fundamental constants in our universe seem to be tuned precisely to values that allow for complex structures. Stars, planets, chemical elements, and the existence of life. If the gravitational constant were just a tiny bit larger, all the stars would burn through their fuel in just a few million years, leaving no time for life to emerge. If the electromagnetic force were slightly weaker, atoms wouldn't be able to form stable molecules. Chemistry wouldn't exist at all. If the strong nuclear force were even slightly different, stars wouldn't be able to synthesize carbon. And carbon is the foundation of all known life. The sheer precision of these constants is staggering. Some are tuned to within 0.00%. Regarding this fine-tuning, mainstream physics offers two explanations. One is the anthropic principle. Perhaps there are countless universes, a multiverse, each with different physical constants. We just happen to live in the one whose constants allow life to exist. Because only in a universe like this would there be someone around to ask the question. The other is a deeper, underlying theory. Perhaps there exists some fundamental theory of physics we haven't discovered yet, explaining why these constants have to be exactly these values. But there is a third possible explanation. These constants were set manually. By whom? By whoever designed and runs this simulation. If you wanted to create an interesting, complex, and conscious simulated world, what kind of parameters would you need to set? It's just like a game designer who knows that to make a game fun, you have to tune the gravity, the friction, and the bounce coefficients just right. Chapter 7. Why fooling 8 billion people is easier than you think. Now, let's answer the core question of the night head on. What if the world is virtual? How could he possibly fool 8 billion people? The answer has several layers. And all of them will shift how you understand the concept of reality. The first layer is, he doesn't need to fool anyone at all. Because you are already a part of the simulation. This is the most fundamental and counterintuitive point. When we talk about fooling 8 billion people, we subconsciously assume that these 8 billion people exist independently outside of the simulation as a reality, and that the simulation needs to deceive them. But if Nick Bostrom's argument is correct, then these 8 billion people are themselves products of the simulation. Their brains, their perception of reality, are all just the results of running code. You don't need to fool a piece of code. When a character in a game thinks the game world is real, it's not because the game is deceiving them. It's because believing the world is real is simply how they were programmed to be. The second layer is, the simulation doesn't need to be perfect. It only needs to be perfect locally. Many people object to the simulation hypothesis, saying the computing power required to simulate the entire universe is way too vast. But this objection is based on a false assumption, that it needs to simultaneously and precisely calculate the state of every single atom in the universe. But an efficient simulation doesn't need to do that. It's just like we mentioned earlier. Exactly like the on-demand rendering principle in game engines. The simulation only needs to, at any given moment, precisely calculate the part that is actually being observed. You have never seen a grain of sand on the third planet of a star on the other side of the galaxy. So, that grain of sand doesn't need to be computed at all. It only needs to exist in a highly rough, approximate form within the background of the simulation, and that's enough. Only when one day, some civilization develops a powerful enough telescope and turns its lens toward that planet, will it need to temporarily render the details of that grain of sand. This strategy of on-demand computing can drastically reduce the computing resources required for the simulation. A world of 8 billion people seems like it would require massive computing power. But what if, at any given moment, only a tiny fraction of the details needs to be precisely calculated? Only the light and shadows in the room right in front of you. Only the temperature of the glass of water in your hand needs to be simulated. Only the line of text you're reading right now needs to be rendered. Then the total amount of computation would drop significantly. The third layer of consistency is achieved through rules, rather than by controlling each person individually. The biggest challenge in simulating 8 billion people. If I see the moon in the east from Beijing, how do you ensure the experience is consistent for everyone? You don't need to micromanage every person's experience. You only need to establish a complete set of physical laws, and let everyone follow that same set of rules. It's just like a game developer. They don't need to manually program every single frame that every player sees. They only need to write the physics engine and the rules for the rendering engine, and then let those rules run automatically. Our physical laws, Newtonian mechanics, electromagnetism, thermodynamics, quantum mechanics, general relativity, might just be the physics engine for this simulation. They don't need to be applied to every single instance individually. They are a set of self-executing rules that ensure every player's experience remains self-consistent. The fourth layer. Your memories are also part of the simulation. But I have memories of the past. I remember things from my childhood. I remember what I did yesterday. These memories prove the world is real. But memory is nothing more than the product of specific connection patterns among neurons in your brain. If your brain is being simulated, then your memories are being simulated too. All your memories regarding the past, your childhood, your first love, the trip you took last year, could have been pre-installed in your virtual brain. You feel like you've lived for 30 years. But perhaps this simulation only started 5 minutes ago. And your 30 years of memories are simply part of the initial settings. The very idea is dizzying. Yet, logically, it's completely irrefutable. You can't use memory to prove that the past is real. Because memories themselves could be manufactured. Anomalies and glitches at the fifth level are automatically corrected by the brain. Even if the simulation occasionally shows a small bug, a tiny inconsistency, or a momentary deviation in the laws of physics, it's highly likely your brain wouldn't even notice. And why? Because, as we said before, the brain itself is a machine built on filling in the blanks and auto-correcting errors. It automatically ignores information that doesn't fit expectations, and automatically rationalizes observations that don't add up. Have you ever had an experience like this? You clearly remember putting your keys on the table, but when you turn back, they're gone. Later, you find them on that very table. How would you explain that? You wouldn't say, the world simulation had a rendering error. You'd say, I guess I just misremembered. Or, maybe they were covered up by something. Your brain will automatically provide a reasonable explanation for an anomaly like that. Because the one thing the brain hates most is admitting that there are unexplainable cracks in reality. Even if the simulation makes small mistakes every day, your brain will jump in to cover for it. The sixth level, social consensus, is, in itself, the most powerful firewall. You believe the world is real, not just because your own senses tell you so, but because everyone around you also tells you it's real. Your parents, your friends, the scientists on TV. Everyone is living in the exact same reality. And everyone, without a shred of doubt, treats this world as real. This social consensus builds an incredibly strong psychological defense. Even if you occasionally feel a seed of doubt, the normal behavior of the people around you will quickly pull you right back in. You won't seriously doubt reality, because if reality were fake, that would mean everyone is lying to you. And that idea is just too crazy. Your logic would instantly reject it. But the irony is, if the world really is a simulation, then the fact that no one doubts it is not evidence that it's real, but rather evidence that the simulation is working perfectly. Social consensus isn't an external check independent of the simulation. It's actually a part of the simulation itself. The fact that 8 billion people don't suspect a thing doesn't prove the world is real. It just proves that if a simulation exists, its social layer is just as successful as its physical one. Chapter 7. The continuity of time is the most clever trick of all. The reason you feel the world is real is because the time you experience is continuous. Every single now flows naturally from the previous one. Your life has an unbroken timeline. This continuity gives you a profound sense of reality. But do you really experience continuous time? Every night when you fall asleep, your consciousness shuts off, yet you never doubt that you're picking up right where you left off yesterday. During those 8 hours you were asleep, who's to say the entire simulation wasn't paused, modified, or even rebooted? Are you, tonight, and you, tomorrow morning, actually the same consciousness running continuously? Or are you just two separate, independent programs that happen to share the same set of memory data? The continuity of time is merely a subjective feeling, and subjective feelings are exactly what simulations are best at creating. Chapter 8. The source code of the mathematical universe. Now, let me share something that keeps many physicists and mathematicians up at night. This world has an extremely strange property. It is written in the language of mathematics. The Hungarian-American physicist Eugene Wigner wrote a famous paper titled The Unreasonable Effectiveness of Mathematics. In the natural sciences, he pointed out a profound mystery. How abstract mathematical concepts, invented by the human mind, to be able to describe the physical world with such precision. Why is it that symbols written on a piece of paper can actually predict the orbits of planets thousands of miles away, the state of the universe billions of years ago, or the behavior of particles inside an atomic nucleus? This precision isn't just an approximation, it's not rough at all. It is accurate to more than a dozen decimal places. It's a gift that demands an explanation. There are many different ways to interpret this mystery. Some people believe that mathematics is a tool invented by humans, and that we only use it because we specifically chose the math that happens to describe our world. Others believe that mathematics is discovered, rather than invented. They argue that mathematical structures exist objectively, and that the physical world follows mathematical laws, because the physical world itself is part of a mathematical structure. MIT physicist Max Tegmark has pushed this idea to the absolute extreme. He proposed the so-called mathematical universe hypothesis. Our physical world isn't just described by mathematics. It is, in itself, a mathematical structure. If Tegmark is right, if the universe, at its most fundamental level, is just a mathematical structure, then where exactly is the boundary between it and a computer simulation? Isn't a simulation just a concrete realization of a mathematical structure? Isn't a program just a set of mathematical rules being executed in a specific sequence? If the essence of the universe is mathematical, then the distinction between saying it is a simulation and saying it is real may not exist at all, because at the fundamental level, simulation and reality are the same thing. This mathematical perspective makes the question of whether the world is virtual fundamentally suspicious. Perhaps the reason this question cannot be answered isn't because we aren't smart enough, or because our technology isn't advanced enough, but because the question itself is meaningless. It's just like asking if water is really wet or virtually wet, if wetness is just H2O. The mathematical description of interactions between molecules, the poetry of the real versus the poetry of the virtual, refers to exactly the same thing. Let's think about this another way. If a simulated creature feels pain, is that pain real? If it's done in the exact same mathematical way as real neurons, and firing produces the exact same signal patterns, then the pain they experience The very concept of real needs to be redefined. Chapter 9. Can we test this hypothesis? After so much philosophy and theory, what you probably want to know most is there actually a way to test whether we are living in a simulation? One of the core principles of science is falsifiability. If a hypothesis cannot even be tested in principle, then it doesn't count as a scientific hypothesis. Can the simulation hypothesis be tested? Some scientists believe it is possible. In 2012, physicist Silas Bean and his colleagues proposed an interesting line of thought. They noticed that physicists, when using computer simulations to study quantum chromodynamics inside an atomic nucleus, the simulation must be carried out on a discrete lattice. Because computers cannot process truly continuous space, this lattice-based space would leave specific imprints on the simulation results. For example, the trajectory of high-energy cosmic rays would show slight anisotropy. If our universe is also simulated on a grid, then the highest energy cosmic rays might also exhibit similar anisotropy. They calculated the expected magnitude of this effect to look for it using existing cosmic ray detectors. This specific anisotropy has not yet been discovered, but that does not mean we are not in a simulation. If we are in a simulation, then the grid scale used by this simulation might be smaller than what Bean's team assumed. Or it might use a completely different computational architecture. This is the fundamental difficulty in testing the simulation hypothesis. Any negative outcome could be interpreted as a simulation that is more sophisticated than we imagine. Another line of reasoning comes from information theory. The physicist John Wheeler once proposed a famous slogan. He believed the ultimate nature of the physical world is not matter. If the foundation of the universe is truly information, then certain fundamental theorems in information theory, such as information not being able to travel faster than light, or information not being able to be compressed without loss into an infinitely small space, could be understood as hardware constraints of a simulation. Some physicists are even attempting, from the perspective of information theory, to derive general relativity and the fundamental equations of quantum mechanics. If they succeed, these could be understood as the rules of information processing. This brings us back to the idea that the universe is a computer. Related to this is the holographic principle in physics. This astonishing discovery from black hole research can be completely encoded on its two-dimensional boundary. Much like the three-dimensional world we live in is actually just something projected from a two-dimensional screen. This is a conclusion of serious theoretical physics, supported by the mathematics of the ADS-CFT duality in string theory. If our three-dimensional world is truly a projection of two-dimensional information, then the boundary between reality and simulation becomes even more blurred. A projected world and a rendered world. How much difference is there, really, in their essence? There is also an even more whimsical, yet logically impossible to rule out, possibility. Perhaps the operators of the simulation occasionally intervene, just like a game administrator might occasionally log into a game server to fix bugs or adjust parameters. The operators of the simulated universe might occasionally intervene in the simulation. To the inhabitants within the simulation, this kind of intervention, it could just be some unexplainable anomalies. It's not that every unsolved mystery is just a simulation bug, but if the world really is a simulation, then those phenomena that seem to defy the laws of physics would have another possible framework for explanation. We also have to admit a cruel reality. A truly perfect simulation is impossible to detect from the inside, just like a prisoner can't see through a perfect cage. If every wall of that cage looked exactly like the real sky, with the air composition and temperature perfectly identical, the prisoner would never realize they were in a cage. This unfalsifiability that simulation theory talks about is exactly what makes it so unsettling. You can't prove it's right. And you can't prove it's wrong, either. It's like a question mark hanging over your head forever. If chapter 10 is true, then what's on the outside? Let's conduct a bold thought experiment. Suppose we really are living in a simulation. Then a natural question to ask is, the outside could be completely different from our world. A four-dimensional space-time with one added dimension of time. But the real world outside the simulation might have a completely different dimensional structure. Some kind of geometric form we simply cannot imagine. Our laws of physics, gravity, electromagnetism, strong and weak forces, might just be rules internal to the simulation. Completely different physical laws. Perhaps there's no such concept as physical laws at all. Just like the gravity understood by a character in a game. Jump height, fall speed. Is something completely different from gravity in the real world. What might those running the simulation be? If we follow Bostrom's framework, they could be our own descendants. A civilization that has reached a post-human stage. They run this simulation, perhaps to study their own history. Just like our historians today, studying ancient Rome, except their research method isn't flipping through documents. But instead, it simulates an entire ancient society directly. Looking at this idea, while it sounds bizarre, it is actually logically consistent. An even more dizzying possibility is the concept of nested simulations. The civilization that runs our simulation might itself be living in another simulation. And the civilization running their simulation might also be in yet another one. It's just like a set of Russian nesting dolls. Layer upon layer. Bostrom himself has discussed this possibility. He points out that if the depth of the simulation is great enough, then at the very bottom level, the ultimate computer running all these nested simulations would require an astronomical amount of computing power. However, if each layer of the simulation is just a little bit simpler than the one above it, with a lower resolution and slightly rougher physical laws, here we find an interesting intersection with religion. If there is a creator outside the simulation, this creator is remarkably similar to God in traditional religions. They can observe everything happening within the world. These attributes are strikingly similar to the descriptions of God. Bostrom himself also noticed this point. He stated that between the simulation argument and theology, there are also huge differences. The most important point is that this creator is, in itself, a naturally existing entity. They are subject to the natural laws of the world outside. They are not all-knowing or all-powerful. And they are capable of making mistakes. There is one more question worth thinking about. If we discover that we are indeed in a simulation, some people's first reaction is, then nothing has any meaning anymore. But if you think about it carefully, why is it that your happiness is real? Regardless of whether it's generated by carbon-based neurons, or by silicon-based chips, your love is real. Whether it happens in the physical world, or within a simulated one, the starry sky you look up at tonight is real. And your experience is everything you have. It never really depends on what the base material is made of. It depends on the depth and quality of the experience itself. A moving piece of music isn't any less beautiful because it's played back from a digital audio file. And it doesn't matter if it happens in a virtual world. This also leads to a profound ethical dilemma. If we truly develop the ability to create perfect simulations, and those conscious beings within the simulation feel fear, experience loss, and face death, this creating a world full of suffering, any different from causing suffering in the real world? Creating a simulation is a massive moral responsibility. And if the ones running our own universe are facing these same ethical considerations, they either believe that the suffering in the simulation isn't real, and therefore doesn't matter, or they have a moral system we simply cannot comprehend. Or, even more unsettling. Chapter 11, The Dissenting Voices. Why are so many scientists not buying it? After introducing so much evidence supporting or sympathizing with the simulation hypothesis, in the interest of fairness, we should also listen seriously to the opposition. Many brilliant scientists and philosophers believe the simulation hypothesis is wrong, misleading, or even dangerous. Their arguments are equally worth pondering. The first objection comes from computational complexity. How much computing power does it take to simulate an entire universe? Let's make a rough estimate. Our observable universe contains roughly 10 to the power of 80 elementary particles. Simulating the quantum state of each particle requires processing an incredibly complex wave function, and the quantum states of multiple particles are all entangled. Computational complexity grows exponentially with the number of particles. The total computing power required for all molecular quantum behavior, and it has already exceeded the limits of all current human computers. It would likely require a computer that is even larger than the simulated universe itself, which seems logically contradictory, to perfectly simulate a system as complex as itself, unless your computational efficiency is unimaginably high. Of course, proponents of the simulation hypothesis could reply, who says a simulation needs to be precise down to the quantum level? Perhaps the simulation only needs to be accurate on a macroscopic level. Just like how we forecast the weather, without needing to track every single air molecule, yielding sufficiently accurate results on a macroscopic scale, using probabilistic wave functions, instead of precise deterministic calculations, thereby saving a massive amount of computing power. This turns into an unfalsifiable catch-all response, which can always be deflected by saying the simulation is smarter than you think. The second counter-argument comes from physicist Sabine Hossenfelder. She points out that the simulation hypothesis is not a scientific hypothesis, but rather a philosophical speculation disguised as science. It needs to make concrete, testable predictions, such as, if we do X, we should observe Y. The simulation hypothesis makes no such predictions. It simply says, maybe we are in a simulation. This doesn't lead to any specific, observable consequences. Any observation can be reconciled with the simulation hypothesis. This result shows the simulation is precise. That anomaly shows the simulation has a bug. The third counter-argument is more fundamental, and involves the nature of consciousness. Bostrom's argument relies on one key assumption, that consciousness can be produced by computational simulation. But this assumption itself is an unproven philosophical claim. Whether consciousness, the subjective experience and ability to perceive pain and pleasure, can truly arise from pure computation, or if consciousness requires some kind of special physical substrate, like carbon-based neural networks to exist. This is what's known in philosophy as the hard problem of consciousness. Currently, no one knows the answer. If consciousness cannot be produced by computational simulation, if a computer that simulates a brain doesn't actually produce any subjective experience, then Bostrom's entire argument is just built on shifting sands. The fourth objection is a pragmatic one. Physicist Neil deGrasse Tyson once said something very insightful. Even if we are truly living in a simulation, it doesn't have any impact on how you should go about your day tomorrow morning. The laws of physics remain the same. Your bank account balance remains the same. The people you love remain the same. The simulation hypothesis might be philosophically interesting, but it doesn't yield any actionable consequences. Pondering whether we're in a simulation is pretty much the same kind of intellectual game as wondering what would happen if the gravitational constant were slightly higher. It won't change your life. The question itself is the answer. Having come this far, you might feel a bit confused or even frustrated. Is this world actually virtual or not? I haven't given you a definitive answer, have I? But perhaps, just perhaps, this is precisely the most profound insight of this topic. Certainty itself might be nothing more than an illusion. Just think about it. Throughout the history of human cognition, how many times have we experienced the collapse of certainty? Ancient people were certain the Earth was the center of the universe. And then Copernicus proved it wasn't. People were certain that space was absolute, and that time flowed uniformly. And then Einstein proved that space could bend. People were certain that the physical world was deterministic. And then quantum mechanics proved that at the most fundamental level, everything is probabilistic. Every single time, humanity has had to abandon a certainty it once thought was unbreakable, and accept a much stranger, yet far more profound picture of reality. Perhaps the simulation hypothesis is the next candidate for the collapse of certainty. It's not that it's necessarily correct, but that it forces us to re-examine an assumption we have always taken for granted. That reality exists independently of our observation. This assumption works perfectly well in our daily lives, of course. Like whether a table is still there when you're not looking at it. But at the deepest levels of philosophy and physics, it might not be as solid as we think. There is a particularly fascinating theory here. If we are truly living in a simulation, then the very brains we use to ponder whether or not we are in a simulation are themselves just part of that simulation. Our ability to reason logically, our physics experiments, all these tools that help us uncover the truth. Can a simulated brain actually discover that it's being simulated? It's like a piece of code trying to read its own source code. Can it really do that? In some programming languages, it's possible. But the source code it reads is still just a result of the program running. It's a dizzying, self-referential loop. But perhaps this very act of thinking, this ability to step outside oneself and examine one's own situation, this urge to ask ultimate questions, is the most remarkable trait of us as conscious beings. Whether the universe is real or a simulation, the fact that we can even ask this question is an extraordinary thing in itself. In the known universe, there is only one thing so far that has achieved this. Human consciousness. That a bunch of atoms or a string of code could actually turn around and question its own essence. And question the essence of the universe that created it. If that isn't a miracle of some kind, I don't know what is. Let me take you through an even deeper question. If the world really is a simulation, then how long has this simulation been running? The universe has existed for 13.8 billion years, the age of the Big Bang. Is that 13.8 billion years itself just a simulation? It could have been started just 5 minutes ago. And the 13.8 billion years of cosmic history, all the cosmic microwave background radiation, it's all just part of the initial conditions. It's like loading a save file in a video game. The game world might have centuries of history, but that save file was loaded just 1 second ago. This is what the philosopher Bertrand Russell called the 5-minute hypothesis. Perhaps the entire universe popped into existence 5 minutes ago, complete with all those fake memories, fossils and starlight, because any evidence you use to refute it, including your memories from 5 minutes ago, could all be pre-loaded as well. This kind of onion layer peeling skepticism gives you a strange sense of vertigo. But I believe this vertigo itself is valuable. It reminds us that our understanding of the world is always temporary, limited, and subject to revision. People once thought Newtonian mechanics was the ultimate truth, until Einstein came along. People 100 years ago thought Einstein's theory of relativity and quantum mechanics were the final theories, but we know now that they contradict each other, and there must be a deeper theory that unifies them both. Perhaps 100 years from now, we will discover a brand new framework that makes the distinction between real and virtual as outdated as the distinction between heaven and earth. That used to be an important conceptual boundary. Now we know that the heavens and the earth follow the exact same physical laws. Perhaps the boundary between reality and simulation will eventually dissolve in the very same way. Epilogue. Falling asleep under a virtual or real starry sky. Our journey ends here. We've traveled from Plato's cave to Bostrom's computer, from the eerie mysteries of the double-slit experiment to the profound depths of the mathematical universe, from the plight of 8 billion minds to the enigma of the nature of consciousness. We didn't find a definitive answer, but we did find some better questions. Let me summarize what we discovered tonight. What if the world is a simulation? Why would it be able to fool 8 billion people? There are many layers to the answer. The shallowest layer is that our senses themselves are imperfect translators. What they give us is never reality itself, but a model constructed by the brain. The brain's power of imagination and autocorrection helps the simulation cover up any tiny glitches. They can act as a set of self-executing rules to ensure that everyone's experience remains consistent. And if we ourselves are products of a simulation, then the very word fool loses its meaning. You don't need to fool a piece of code. The most important realization may not be whether the world is truly a simulation or not, but rather a much warmer truth. No matter if the world is built from carbon atoms or lines of code, the peace you feel when you hear the wind outside your window is real. The warmth that rises in your heart when you think of someone far away is real. Even if the entire universe were a meticulously crafted simulation, the texture, depth, and weight of these experiences would not diminish by even the slightest bit. You don't need any external guarantee to prove your own value. The experience itself is the value. It's late at night, and the starry sky outside your window, whether it consists of real stars or just simulated points of light, is slowly rotating above your head. The Milky Way, whether it is 200 billion real stars or simply a ribbon of light rendered by the graphics card of some supercomputer, is flowing across your sky with the same beauty right now. Whether it is light reflected off the actual lunar surface, traveling 380,000 kilometers through space to reach your eyes, or a simulation program, calculating the output of a lighting equation, based on the virtual coordinates of the sun and the moon, it is shining down with the same gentleness at this very moment. Perhaps through the experiment of some genius, perhaps through some groundbreaking mathematical proof, or perhaps through some method that we cannot even begin to imagine right now. But that's a story for the future. You only need to know one thing. Right now, you exist. Whether that existence is carbon-based or digital, whether this universe is real or virtual. You, who are curious, thinking, and imagining, You, who are slowly feeling the sleepiness creep in. You are one of the most remarkable beings in this universe. Because you have the power to wonder. Go ahead, close your eyes. Let those questions about what's real and what's virtual drift like a sky full of stars, slowly spinning in your mind, until they finally melt into the warm darkness. Perhaps in your dreams, you will fly to the edge of the universe. Reach out and touch that thin film separating the inside from the out. Maybe you'll find it's thinner than you ever imagined. Or maybe you'll find it isn't even there at all. Regardless of the universe you inhabit right now, when you wake up tomorrow, the sun will rise just as it always does. Whether it's real or a simulation, but it will feel just as warm.